My dear students, welcome to Easy BTech, your guide for BTech and beyond. Our subject signals and systems. And in this session, we are going to discuss topic orthogonal signal space, evaluation of mean square error. Okay. Before going to start our session, all of you please subscribe, share the channel. Very helpful to you. It is sure very helpful to you. Let's start our session. So already we have seen orthogonal signal space in the previous session. Just I will repeat once again. What is meant by orthogonal signal space? We consider a function x of t. We take a signal x of t, right? This function is represented using this function x of t is represented using n number of mutual orthogonal functions, small n number of, like g1 of t, g2 of t, and so on, gn of t, n number of mutually orthogonal functions over the interval t1 to t2, over the time interval t1 to t2. T1 to T2. So in this topic, we have seen how to calculate the formula or coefficients Cj. So Cj we already derived. I am writing once again, integral T1 to T2, integral T1 to T2, x of t into Gj of t, Gj of t dt, divided by this total divided by integral t1 to t2, integral t1 to t2, gj square of t dt, gj square of t dt. So here the denominator integral, what is the denominator integral we have here? Integral t1 to t2 gj square of t dt. This I am taking as a constant like kj. The value of this denominator integral is, take it as kj. Then the cj will become, or cj into kj. So this denominator I am sending left, it will become into. So cj into kj is equal to integral t1 to t2 x of t gj of t, gj of t dt. So this is the point. It will be useful. This integral is useful, or cj kj is equal to integration t1 to t2 x of t gj of t. It is useful whenever we are going to see mean square error. Okay, so that is why please remember this point whenever we are going to see mean square error. This is useful. Right? Now we are going to discuss now the topic orthogonality in complex signals. Orthogonality where in complex signals, in complex functions or complex signals. So till now we discussed orthogonality in real signals. Now the topic is orthogonality in complex signals. So in the same way as we discussed in real signals, the same way we discuss this topic. Let's consider complex functions, two complex functions or signals, complex signals like x1 of t, x2 of t. They are complex signals. These two are complex functions or complex signals. Now the concept is approximate x1 using x2 or in terms of x2 with minimum error. Approximate x1 in terms of x2. Approximate x1 or x1 of t in terms of x2 of t. In terms of x2 of t with minimum error. With minimum error. With minimum error. So how to write it with minimum error? So how to express this? This is the way. How to write x1 of t is equal to some constant c12 into x2 of t plus the error function xe of t or error signal xe of t, as like in real signals. The same way we are writing. So x1 of t written in terms of x2 of t with minimum error. This is the way. So here after writing, after approximation, what we need to do, we need to calculate what is C12 value. This coefficient is how much. That is the meaning of approximate x1 of t in terms of x2 of t. We have written x1 using x2, but what is C12 here? That is a point we are going to see. So in case of real signals, already we discussed this C12. In case of real signals, what is C12? Coefficient C12 or constant C12. So integral T1 to T2 x1 of t into x2 of t dt divided by integral T1 to T2 x2 square of t dt. This is the formula of C12. Now in case of complex, we have complex functions now, complex signals now. The difference is very small, almost same. C12 is also almost same. A very small difference, that is C12 is equal to numerator integral T1 to T2 x1 of t into x2 star of t dt divided by integral T1 to T2 x2 of t into x2 star of t dt. So here if you observe C12 formula, here we have for the second signal x2 star of t. What is x2 star of t? Complex conjugate of x2. x2 star of t means what? Complex conjugation of x2. The signal x2. Complex conjugation of x2 or x2 of t. So here we can also take complex conjugation for x1 also. So or in this way also we can write. So what is that? C12 is equal to integral T1 to T2 x1 star of t into x2 of t dt divided by integral T1 to T2 mod x2 of t or magnitude of x2 of t square dt. So both are same meaning. The C12 formula here and C12 here, both are equal, same. So here one point I want to mention is, if you multiply x2 of t by x2 star of t, this will become magnitude x2 of t whole square. This is the point. So that is why the denominator integral x2 star is equal to magnitude of x2 of t whole square, that I written. So this is complex orthogonality of complex signals. Here C12 we are calculating approximation of one signal in terms of another signals. Now, what is orthogonality here? Orthogonality of complex signals means what? C12 value that depends upon C12 value. If C12 is equal to 0, the C12 value is 0. Then C12 is equal to 0 means which will be 0? C12 formula, you know, numerator integral, denominator integral. So C12 value 0 means the numerator integral. What is the numerator integral? You can take anyone. Here we have two options. So integral T1 to T2. I am taking first option, x1 of t into x2 star of t dt. If this integral is equal to 0, what is the meaning of this integral is 0? Integral t1 to t2 x1 of t into x2 star of t dt is equal to 0, which means C12 value 0, which means what it means? The two signals, complex signals x1 of t and x2 of t, both are orthogonal signals over the interval t1 to t2. They are orthogonal functions over the interval t1 to t2. So this is about orthogonality in complex signals. Orthogonality in complex signals. Next we are going to see, the next is approximation of, very important topic it is, and easy topic. Approximation of a signal or function, x of t. Approximation of a signal or function x of t using n number of or n mutually orthogonal functions, n mutually orthogonal functions or signals approximation of a signal x of t using n mutually orthogonal functions or signals, and this n mutually orthogonal functions are complete set of functions, complete set of mutually orthogonal functions. So here I want to stress on complete set. So using complete set of n mutually orthogonal functions, that is a topic. Complete set of n mutually orthogonal functions. Complete set of n mutually orthogonal functions, n number of, right, n mutually orthogonal functions or signals. So complete set, what is a complete set? That I want to tell now. So let's consider n number of mutually orthogonal functions. We take the set of functions like 10 or 20 in that set. They are mutually orthogonal. So consider, take n mutually orthogonal functions, orthogonal functions over the interval t1 to t2. Over the interval t1 to t2. Over the interval t1 to t2. t1 to t2. So this set I am taking now. Let the set is g1 of t, g2 of t. These are mutually orthogonal functions. N number we have. So that set I am writing mathematically. g1, g2, g3 of t, and so on, gn of t. So n number of mutually orthogonal functions. They are mutually orthogonal over the interval t1 to t2. Over the interval t1 to t2. Now this set is, the question is, this set is complete set or not? That is a point now. Complete set or not? Complete set or not? So how to define complete set? This n number of mutual orthogonal functions we have. This set is complete set or not? So how can you say this is a complete set or not? Or incomplete set? So complete set means, I am writing now, complete set means, suppose if you take a function, another signal or function, another signal like y of t is a outside signal, not in the set. This y of t is a outside, not in this set g1, g2, g3, gn. So this is a any function or outside signal y of t. If you do this integral t1 to t2 y of t into, here we have n number of functions. So like gi of t or gj of t or gn of t, anyone, gn of t dt. So if you perform this integral over the interval t1 to t2, you take this outside function, we are taking this outside function, we are doing integration with any one of this set, either g1 or g2 or g3 or g4 or like. If you got the answer 0, if you get the result 0, then this y of t is also will become a member of orthogonal set. It will become a member. We can include this y of t in g1 set, g1, g2, g3. So it will become member of set, one member of set or member of set. And the set is said to be not complete because y of t is existing like this. A outside function is existing like integration g1 to t1 to t2 y of t gn of t dt is equal to 0. So then this y of t will become a member of the set, and set is said to be not complete. The set is not complete set. So when it will become complete set? Whenever if you not possible like this, whenever the integration t1 to t2 any function y of t into gn of t dt is equal to 0. So this type of function not exist like this integral. So y of t should not exist like integral t1 to t2 y of t into gn of t dt is equal to 0. So y of t should not like integral t1 to t2 y of t gn of t dt is equal to 0. So whenever it is possible, then the set will become complete set. So y of t should not exist like integral t1 to t2 y of t gn of t dt is equal to 0. Then the set will become complete set. If it is 0, the y of t will become member of the set. If y of t should not exist like t1 to t2 y of t gn of t dt is equal to 0, then the set is called as complete set. So there is no confusion. If integral is 0, it will become a member and set is said to be not complete. If not exist, y of t not exist like t1 to t2 y of t gn of t dt is equal to 0, then the set will become complete set. So this is the meaning of complete set. Very, very important point. Okay. Next thing, we are going to discuss mean square error, evaluation of mean square error. It is also important point, important topic. Evaluation of mean square error. How to calculate mean square error? Mean square error. So we are representing this mean square error by the symbol epsilon. So how to calculate mean square error? That is the topic we are going to see now. So already we know mean square error definition, we know epsilon, we know. We know that MSE, mean square error, epsilon is equal to 1 by T2 minus T1 integral T1 to T2 integral T1 to T2 error square, that is xe square dt. This is a mean square error. As the name itself, so square error, we have square error, mean, so integration of square and dividing by T2 minus T1, dividing by the interval or duration or time T2 minus T1. It will give mean square error. So here, what is xe of t? Error signal. So we know error signal. That is also we know. We know that error signal xe of t is equal to, or error function xe of t is equal to x of t minus summation I is equal to I or j. You can use anyone. I is equal to 1 to n c I square. So I am taking j for convenient. C j square. Okay. Sorry, j is equal to 1 to n, not square, only cj. Y square will come. Cj, and here Gj of t. Cj, Gj of t. This is the error function. How it came, this error signal, how I written? Actually, x of t we can write like C1 G1 of t, C2 G2 of t, and C3 G3 of t, and so on. Cn Gn of t. We have n number of mutual orthogonal functions. So Cn Gn of t plus error xe of t. So from this we can write xe of t is equal to x of t minus this plus we can write as summation. So summation j is equal to 1 to n cj gj of t. Right? And we know cj formula. We know the formula of cj. We derived it. Cj is equal to integral t1 to t2 x of t into gj of t, x of t into gj of t dt divided by integral t1 to t2, here gj square of t dt, gj square of t dt. And we can take the denominator integral, this denominator integral as a constant kj. The value is kj. Then the numerator integral will become, what is the numerator integral? Integral t1 to t2. The numerator will become, or numerator integral is equal to cj into kj. We can use it in this mean square error evaluation. That is why I am telling here. So already we discussed, again I am saying, because it is useful now. So this is the error function. This error function we are going to substitute in mean square error. Right? After that, what happens, we will see. So epsilon will become now 1 by t2 minus t1, 1 by t2 minus t1, integral t1 to t2. What is the error function here? We have error signal, we have x of t minus summation j is equal to 1 to n cj gj of t whole square we have. So So whole square dt, right? Just I substituted error function or error signal. This we have now. So if you see it, if you observe it, it is like a minus b whole square. Now I am going to open it. I am going to expand it. So let's see now. Epsilon is equal to 1 by t2 minus t1, 1 by t2 minus t1, integral t1 to t2. So first thing, a square, that is x square of t, and b square plus summation j is equal to 1 to n b square. Here what is b here? Cj gj. So cj square gj square of t minus 2ab. So minus 2 summation j is equal to 1 to n. A is x of t and b is cj gj of t minus 2ab it is. Integration dt. Okay. Now we are going to simplify it. So here we have three terms. This is the first one. Just I am giving numbering for clarity. This is the second term, and this is the third term. So here we have cj square, which is a constant. So integration t1 to t2 gj square of t dt, right? So I will write separately. 1 by t2 minus t1, 1 by t2 minus t1. So what is the first term? Integral t1 to t2 x square of t dt. Just I am separately writing the integration. We have three terms, writing integration separately, right? Next, the second term plus summation j is equal to 1 to n cj square. So integral t1 to t2 gj square of t dt. This is the second term. And third term minus 2 summation j is equal to 1 to n cj, and integral t1 to t2 x of t into gj of t dt. So these are the three integrals we have, right? Now just a simplification. So already we know that this integral term, this integral t1 to t2 gj square of t is, we have taken as kj, right? This integral is kj, just before we discussed. And this integral also we discussed. The integral t1 to t2 x of t gj of t, it will become cj into kj. This integral will become. So this substitutions we are going to see now. We are going to take. Now epsilon will become 1 by t2 minus t1, 1 by t2 minus t1, integral t1 to t2 x square of t dt. This is as usual first term, plus a summation j will be 1 to n, or j is equal to 1 to n cj square. This integral is kj, so I am writing cj square kj, and minus 2 summation j is equal to 1 to n, here cj kj, it will become cj square kj. That's all. So if you observe these two terms, summation j is equal to 1 to n cj square kj minus 2 summation j is equal to 1 cj square kj. So we can subtract these two. They are similar terms. Let's go to that subtraction and write the final answer. So epsilon will become, epsilon is the mean square error. It is 1 by t2 minus t1 bracket t1 to t2 integral t1 to t2 x square of t dt. So minus summation j is equal to 1 to n cj square kj. This is the answer. For example, in problems, evaluate mean square error, right? Using two mutually orthogonal functions. How many orthogonal functions? He is telling two mutually orthogonal functions. So then formula is 1 by t2 minus t1 over the interval t2 minus t1 only. So 1 by t2 minus t1 integral t1 to t2. This is bracket x square of t dt. So minus, here we go for up to, what is the n value here? 2. That is a meaning of two mutually orthogonal functions. So if you open the summation, c1 square k1 plus c2 square k2. Here we stop. Don't write up to c3 square k3 c4 square, because two mutual orthogonal functions only. He will say. That is why the formula is up to c1 square k1 plus c2 square k2. So this is the evaluation of mean square error. Okay. So by this topic, all the topics in the first unit, signal analysis, is covered. In the next session, we are going to discuss numericals or problems, very, very important. So in the first unit, what are the problems we have? So how to solve that problems, we can discuss in the next session or in the next class. So all of you, please watch videos continuously, like, share. Thank you friends.